Today, we're going to talk about the Lineweaver-Burke equation and its function in enzyme inhibition determination. The Lineweaver-Burke equation is a double reciprocal representation of the Michaelis-Menten equation, which has been algebraically transformed so that the axes become reciprocal values, the y-intercept becomes 1 over v max, the x-intercept becomes negative 1 over km, and the slope becomes km over v max. This video will show how the Lineweaver-Burke equation is used for determining the type of inhibition occurring in an enzyme. Reversible competitive inhibitors compete with a substrate by binding at the enzyme active site. The apparent Km increases by a factor of alpha due to the competition of the inhibitor with the substrate at the active site. Competitive inhibitors leave Vmax unchanged, meaning all plots will share the same y-intercepts of 1 over Vmax. Uncompetitive inhibitors bind only to the completed enzyme substrate complex at a site separate from the active site. Apparent Vmax and Km are decreased by a factor of alpha prime, which differs from alpha as it is governed by the binding of the inhibitor with the complex. Lineweaver-Burke plots of uncompetitive inhibitors will share the same slope since values are corrected by alpha prime with different x and y intercepts. Mixed inhibitors are able to bind both enzymes like competitive inhibitors and enzyme substrate complexes similar to uncompetitive inhibitors at a site distinct from the active site and are named for their mixture of effects. They decrease Vmax and can either increase or decrease Km depending on the value of alpha and alpha prime. Plots of mixed inhibitors will all have different slopes and intercepts but will converge on at least one point. Non-competitive inhibitors combine enzymes or enzyme substrate complexes similar to mixed inhibitors, but they are a rare form of mixed inhibition in which alpha is equal to alpha prime, leaving Km unchanged. Apparent Vmax decreases by a factor of alpha prime with increased inhibitor concentration. Plots of non-competitive inhibitors will have the same x-intercept since it is equal to negative 1 over Km, but they will have different slopes and y-intercepts. Plots of non-competitive inhibitors will have the same x-intercept since it is equal to negative 1 over Km, but they will have different slopes and y-intercepts. Generally, mixed and non-competitive inhibition only occurs in enzymes with more than 2 substrates. Illustrated here are 3 Lineweaver-Burke plots for an inhibitor at varying concentrations. Using the figure, determine what type of inhibition is most likely occurring and why. Clearly show each component of each linear equation corresponding to the Lineweaver-Burke equation. And based on your answer from part A, determine the Km of this reaction. Since all 3 plots share the same x-intercept, which is equal to negative 1 over Km, this means they all have the same Km value, indicating non-competitive inhibition. For part B, the y-domain is 1 over v0, the slope is Km over Vmax, and the y-intercept is 1 over Vmax. For part C, solve for the value of the intercept at y equals 0, then solve algebraically. The value you receive will be equal to negative 1 over Km. Once Km has been determined, Vmax can also be easily determined using either this equation or the Michaelis-Menten equation. This is the Edie-Hofstee equation, an algebraically transformed version of the Michaelis-Menten equation, similar to the Lineweaver-Burke equation, but with a slope of negative Km and a y-intercept of Vmax. This is the Edie-Hofstee equation, an algebraically transformed version of the Michaelis-Menten equation, similar to the Lineweaver-Burke, but with a slope of negative Km and a y-intercept of Vmax. In order to solve this problem, we need to do some algebraic rearrangements. Since we already know what the equation for a competitive inhibitor looks like in the Lineweaver-Burke form, we can do a similar rearrangement to get a comparable Edie-Hofstee equation. After following these steps, we can see the effects of a negative alpha correction factor in at least one slope. The x-intercept does not change, but the slope must now be steeper. This leaves by process of elimination line A as our competitive inhibitor, according to the Edie-Hofstee equation. This leaves by process of elimination line A as our competitive inhibitor for the Edie-Hofstee equation. Thanks for watching.